The aim of this chapter is twofold. First of all, I want to show you that there's a lot of things happening in the field of camera-based reconstruction and 3D from images, multi-view reconstruction. But secondly, I want to show you potential areas that might be of interest to you for doing a thesis, maybe a master thesis or something. And so this is why I decided to, in this class, more than ever, bring in a lot of recent developments. In two ways. First of all, I'll give an overview of recent developments that is happening. And in addition, I've asked quite a number of my students to prepare short research presentations where they can highlight their own research in the field and maybe advertise possible master thesis topics that could connect to them. And so, for example, tomorrow we'll have a class where I think 3 of my students will be presenting research, current research from their research. And we'll do more of that in the coming weeks. I talked about SLAM, structure from motion, visual SLAM. This was one work, this LSD SLAM. I also talked about direct sparse odometry. Here's the direct sparse odometry, so methods that can recover the movement of the camera and the 3D structure of the world in real time at very high precision. Now what you can do is you can take these systems and optimize them in many ways. This is just an off-the-shelf gray value camera that we have running here. But obviously, once you were to go into robotics applications or applications of self-driving cars or autonomous drones, things like that, something we do a lot and we have been doing for decades, then you might want to put more sensors, right? And so, for example, in one of my last startups, Artisans, we developed multi-sensory systems that typically have 2 cameras that are synchronized, time-stamped, calibrated. They have inertial measurement units on board, possibly even GPS information. And then all of this information is gathered, and then you can create real-time algorithms of spatial AI that run either on board or in the cloud to process all this data. And obviously, if you tap into more sensors, then you can boost both the precision and the robustness of these systems. So here's one example. This is a system that Lukas von Stumberg developed in my team. It's called delayed DMVIO in short, and it tackles the problem of tracking a camera with an IMU. So very much like what you have on your smartphone. You have a camera and you have an inertial measurement unit. Inertial measurement units are akin to what humans have in their ears, what's called the vestibular system. It tells you something about your orientation, about accelerations. And that is the system that is responsible if you throw up in the car, like I used to do as a kid and like my boy does nowadays, right? And why does that happen? Someone explained that to me. It's very interesting. You drive in the car, and let's say some of you may be familiar with that. Let's say you sit in the back of a car and you read a book. And then you go, say, to downtown, I don't know, Rome. In that way, who would get sick at some point? Show of hands. Yeah, it's about half of the people, I would say. In our family, I can see it's not everyone. My son throws up, my daughter doesn't throw up, beats me. Why one is like this, the other one not? And I've always wondered, because I threw up a lot in the car when we drove around as a kid. And so I've always wondered, why is that? And then one day someone explained it to me. So what happens apparently in the human is that you have multiple senses that tell you about the world. And that's in this case in particular your eyes that tell you how you move from parallax, and then also the vestibular system that measures your accelerations and tells you how you move. If these 2 senses don't match, because you read a book and from the book your eyes tell you you're not moving, but your vestibular system senses the car motion, then the senses don't align. There is one case when senses don't align, and that's when we eat something poisonous. And so evolutionarily, when, I've always wondered, how did we humans come about? We go through this world, we see all sorts of plants. How do we know what's edible and what's not? You grow up, your parents tell you, but what if you grow up in nature as a wild animal? You don't have parents saying that you can eat, that you cannot eat. So you nibble on something and it might be poisonous. What happens? Your senses start to diverge. And so the instinct, the reflex is to throw up poison out of the system. And so it's a very natural instinct that when our senses diverge, we start to throw up. Meaning, I guess, those people of you who throw up in a driving car, you're a little bit closer to your ancestors evolutionarily than the others. But as humans, we use all our senses to localize ourselves in space, and so we can ask, can we do the same with a system that has a camera and an IMU, like on your smartphone? This is called visual inertial odometry. And what Lucas developed, and this is demoing here in the building, right? He's on the second floor, he walks around, he goes up to the third floor, and then he goes into the slides. We often go into the slides when we evaluate algorithms. And in the slides you can see it's pretty dark halfway through. Visually there's very little structure because it's just very shiny, right? And still this system can track at completely unprecedented precision. There is no other method. When we evaluated, there was no method that could do what he could do. As you can see, he goes down 3 floors, up 3 floors, back through the corridor he came from, and there is hardly any drift, right? It's very precise, things line up. And this runs in real time, and it runs indoors, it runs on a car. So a visual inertial system is super useful because it's plug and play. You can just, and sensory-wise it's very small. All it needs is one camera, one IMU that is very lightweight, very small, very cheap also. So you can plug it anywhere and this will track and map the 3D world at very high precision here. So you can do Pokemon on a completely new level now, if you really care about Pokemon. And then you can also deploy these sensors on cars, and we did that extensively, and this is a project where we deployed them on a whole fleet of cars, and we drove, I think, 8,000 kilometers of road, and we mapped the whole large world and its semantics. So what you see here is the drivable area, the sidewalks, the cars, buildings, vegetations. So we can tap into neural networks that can run, say, in the cloud and process all this data semantically. And this is very useful because you can map the 3D world with very cheap camera-based sensors in real time. So you don't need a LiDAR sensor, you can just put cameras and map. And you can extract semantics. The semantics are important for self-driving because you want to know where's the drivable area, where are the sidewalks, where are potentially pedestrians, cyclists, you name it. And we can extract all of that, and neural networks are very good nowadays to extract semantics from images. What we do here is we can label not images but the 3D world that we see through these images. And I think what we did in this project is we went an entire step further into what should really be done. Computer vision for the longest time was constrained to processing images. And the truth is, in most applications, we don't care about images. We care about the world behind the camera or in front of the camera. And this is what we can get here. We can semantically understand the 3D world, and what makes it happen is SLAM. The question is whether we evaluated the positional accuracy. Yes and no. What we always focused on is the accuracy at which we can track the position of the camera. A separate question is how accurate is the 3D world that we recover. I believe it's slightly less accurate, but I would say sufficiently accurate to enable self-driving. So it should be in the range of centimeters. But I do believe if you want super precise surface structure, then maybe the LiDAR is still more accurate because it tends to give you millimeter precision. But then the question is, if you want to avoid an obstacle on the street, do you really need millimeter precision, or is a precision in the range of 1 or 2 centimeters not sufficient? And I think we are at a level where the accuracy is good enough to enable driving. And so a lot of the technologies we developed here on real-time semantic mapping were designed to advance self-driving technologies. A bit more maybe about, I talked about neural networks now. I haven't actually touched on neural networks in class much, but they have revolutionized computer vision for the last 13 years. And it all started for the computer vision community with this data set called ImageNet that a friend and colleague of mine, Fei Li at Stanford, put out with her students. It's a data set many of you will know. It contains millions of images of different objects. Most of these objects are familiar to humans, like this one you probably recognize what the object is. There's always one dominant object. Anyone? What is the dominant object here? A dog. Which one? It's important because there's different dog breeds. Dalmatian, exactly. The thing with the black dots. How about this one? Does anyone recognize what category of objects that is? That's harder, right? It's not a dog, it's some plant. Which one? Anyone? Physalis, yeah, that's what it's called, exactly. This is a fruit, but it's not so common in Germany. When I grew up, we didn't have them, for example. Now you can get them. But as a result, plus if you see them on a tree, most people just see them in a box in the supermarket. We don't usually see them on trees, or it's not a tree, probably it's a bush or something. And so humans are notoriously not so good. And so as a result, even humans, when asked to classify what is the object, they will invariably make mistakes, at least when you talk about the average human. And so what people did for the longest time is they put out this challenge: can you devise an algorithm that says what is the object in the image? And there was a limited number of classes for the algorithm to choose from and for the human to choose from. And then, whereas the best algorithms in 2011 would make 26 errors on some set of data, humans, the average human, would only make 5 mistakes. And that was a massive gap between machine performance and human performance. And that was one of the biggest riddles in computer vision as to, can we ever achieve human level performance? And now if you see the whole history of AI, right, for decades, humans have tried to build machines that exhibit some form of intelligence, right? And then you can start with things like chess playing, but then, you know, humans were not designed to play chess by evolution. We don't come into this world and can play chess. And for any of you who have learned chess, you know, it's a very hard learning, right? It takes years and years of practice and practice so that humans can actually play chess. In contrast, recognizing things with our eyes is something that we are born to do. That by evolution we were trained over thousands of years to understand the world around us with our eyes. Why? Well, the better you can detect the lion in front of you, the longer you live. It's a very strong, you know, evolutionary drive that drives people to recognize things in their world, even camouflage things, right? And so this, for me, is the real intelligence that we need to somehow beat, that capacity to understand the world with our senses. And so as a result, I would argue that computer vision is really the core of artificial intelligence, more than anything else. Why? Because for humans, the visual sense is the dominant sense. 50% of the brain of mammals is basically constantly processing visual information. Half of your cortex is working on visual information processing. That tells you two things. First of all, it tells you it's important, otherwise we wouldn't dedicate half of our brain power on this challenge. And secondly, it shows you it's not easy. Otherwise we could dedicate 5 neurons and be done with it, right? But it's difficult, recognizing things, understanding the world, perceiving things. And reproducing that capacity is really computer vision, and so this is one of the core challenges. And so in 2011, the community felt like there's no way we can ever get nearer human level performance. And then something almost magical happened. Alex Krzyzewski and collaborators around Geoff Hinton proposed to apply a deep neural network. They'd been around, they'd been refined over the years. There were a few people who worked on this. I should say, I don't know if I mentioned that, but in the late 90s, I came from physics. I wanted to change. I wanted to do something that impacts the world. And so in 97, when I was done with a master's in physics, I turned to what can I do next? And I decided neural networks. I was fascinated with that topic. I found it super exciting, the capability to reproduce human cognition and perception and things like that. And so I reached out to many people, including Geoff Hinton. I remember sending him an email in 97 saying, "Dear Professor Hinton, I want to do a PhD in neural networks. Are you looking for people?" He didn't reply to my email. I know that for a fact. Nowadays, if I say someone didn't reply to my email, most of the time it turns out I just didn't read the reply because I get so many emails every day. But back then I didn't get hundreds of emails a day, so I know for a fact he did not reply to my email. And maybe I should have persisted and sent follow-up emails. I didn't. But I sent emails to other people in that field, and some of them did reply, and they said, "Young man, you seem quite talented. Why do you want to go into an area that is completely dead?" I was shocked. This was 97. It was really the winter of AI, maybe the second winter or third, depending on how you count, right? And I was very disappointed because I did believe in deep networks, in neural networks. They were not deep at the time, but I did believe in this approach of neural networks. And so I actually didn't listen, and I went into neural networks anyway. But not with Geoff Hinton. And this is a work of Geoff Hinton's team where they showed that with a deep network, where you probably know how they work, you get the image information coming in from the left, and then layer by layer, it's processed through different filtering and pooling steps. And then on the right side, at some point, you get a classification out. And the idea is that you can train with supervision or some form of self-supervision, you can train the weights so that it does the best classification. And initially these networks were designed to do classification. And what you see, the AlexNet, as is nowadays called, based on Alex Krzyzewski, the first author, this had a massive boost in performance from 26 to 16.4. And so the whole world, my entire community pivoted into neural networks, saying, wow, there is a somewhat new formalism that seems to be very promising. And so they devised deeper and deeper and more sophisticated architectures over the year, such that around 2015, 16, we were able to outperform even the human on a task which I would argue the human was designed for by evolution. And so for me, this slide marks the real breakthrough of AI, of being able to beat the human, not on an artificial challenge like chess playing, but on the challenge that the human was designed for. Now that's not the end of the story, of course, right? Because beyond just seeing that there is a lion, humans can do more. They can anticipate what the lion is going to do next, how it's going to move, things like that. And they can anticipate what might be the best reaction to survive, etc. So humans have a lot of skills that to date machines do not have, right? And so there's still room for improvement, but at least On a specific challenge of recognizing things, we managed to beat the human. Now, that said, for some reason, detecting objects in images, I've never found that fascinating. I don't know what it is, but whether there's an airplane or a cat or a dog in the image, I don't really care about that challenge, and so that's never been my thing. But what I care about, and what we started looking into, my team and many others in the world, is following the 2012 paper, is what else can we do with neural networks? What other challenges can we tackle? And so, for example, in 2015, we started around 2014 working on deep networks for many things. And then in 2015, we showed that you can do optical flow estimation with neural networks. And this is, I believe, the very first work that does optical flow with a deep network. And so, not surprisingly, we called it FlowNet. And pretty much any optical flow algorithm today goes back to that FlowNet paper. And we went further and showed that also problems, this is, I should say, not our work, but we also had other works in showing that you can do stereo and scene flow and other things with deep networks. This is work from my colleague Roberto Cipolla in Cambridge. It's called SegNet. It does segmentation of images. And you see also came out 2015. So all of these low-level image analysis tasks of segmentation, optical flow estimation, stereo, etc. We showed that you can solve them with deep networks. And we also showed for problems like this one, protein prediction. This is also 2016. We showed that you can train deep networks to predict the protein structure. And if you followed the news, you will know that this recently got the Nobel Prize. To our dismay, the AlphaFold team never cited our work, even though we were 2 years earlier. Here's another example from my team, video object segmentation. And you can see we can track objects really pixel precisely in complex videos with neural networks. But coming back to the topic of this class, one of the questions that emerges is, can I leverage deep networks for 3D reconstruction? And to some extent, one can say in the field of computer vision, 3D has, up until this year, remained the holy grail for classical methods. There have been learning-based approaches. These are examples of learning-based approaches that started appearing around 2017-18 for simultaneous localization and mapping. Most of them show you can do it with a deep network, and all of them do not exhibit state-of-the-art performance. So you can do it, but you don't get better performance than with what we already had. The SLAM approaches like LSD, SLAM, and DSO that my team and other teams developed, they were just better. They were faster, they didn't need training data, and they got more precision and more accuracy, more robustness than the learning-based approaches. Why that was is a little bit hard to say, but in a way, taking a set of images from a video and throwing them into some black box deep network and hoping that magically this will give you the trajectory and the 3D world is maybe too much to expect, right? Maybe it would take too much training data, right? Because you would maybe expect it would need training data of all sorts of 3D worlds observed with all sorts of cameras in all sorts of movements, and that's just too much of a multiplicity. Maybe millions of images wouldn't be enough to train it, I don't know. So in a way, the challenge was to constrain it appropriately and to deploy deep networks such that you actually outperform the baseline methods. And this is what we set out to do in this work. So this is work where we built up on neural networks that can predict depths. So it turns out, this is one example from 2017 by Kuznetsov and collaborators. Turns out, given a single image, you can predict the depths. And now you'd say, well, how can that be? Well, how do I know how far things are? In principle, I don't, right? And they could be at any distance. But in practice, obviously, when you train a certain scenario like self-driving, you know, the cars, the objects, the lanterns, the things I see, they all appear in a particular size. And so I know if I see, even for a human, I could ask you how far is that car, and you could tell me, right? Maybe not centimeter accurate, because humans are never good with numbers, let's be honest, but you could say some 10 meters or so, right? And so what I can do is I can train a neural network to do exactly that. I can train it in a supervised way, for example, or this is what we did in this series of papers in a self-supervised way. How does that work? Well, we assume we have a stereo camera system in the car. And that means we can we can say find a depth of the scene such that if I project the colors into the world and back out into the other camera, I should get color consistency. And so much like in the SLAM approaches, this brightness or color consistency, we can use it to train depth prediction in a self-supervised way. Meaning we don't need ground truth, meaning we don't have to carry a LiDAR scanner along to tell us what was the actual distance. We can use the stereo setup, and that means it's cheap. Stereo cameras are cheap. You just plug them in a car, you can drive for days, and you can create infinite amounts of training data. And so in general, the key challenge that I see in the scientific community these days is to develop self-supervised learning techniques that don't need ground truth. And as you can see, our deep network predicts very crisp depths, much better than baseline methods. And then we went further. We took these depth predictions and we fed them into a SLAM approach. So we had an optimization approach like DSO or LSD SLAM, and then we feed all these predictions into the SLAM pipeline. More specifically, we say, given two consecutive images, IT and IT prime, train a neural network to predict the depths for each image, to predict the relative camera motion between the two frames, so a pose prediction, and we also train a network to predict an uncertainty. And then we feed all of these predictions into a SLAM pipeline. More specifically, we predict the depths, we predict the relative camera motion, so T stands for translation and rotation of the camera between the two frames. And once we can do the camera alignment based on this rigid body motion, we can warp the two images and align the brightness values, and then we can have a residual for training this system that is self-supervised. So that is basically saying the colors of these images should coincide. Once I project into the world and back out into the other camera, I can measure the color discrepancy or brightness discrepancy, and this is the residual I use to train these networks. Once you do that for a real camera, it actually doesn't work, right? Because real cameras have aperture changers, so the same image, once I warp it, then the brightness is very different, as you can see here. It's the same image, and for humans it looks like the same, but if you compare the actual brightness values, they're very different because the aperture changed. But what's nice is you can also train a network to predict an affine brightness correction for the whole image. An offset and a scaling of the intensity to make it most consistent with the other image. And what's nice is you can train the network to predict these two parameters that model that correction. And then you have consistent brightnesses that you can use as a residual for training DepthNet and PoseNet. That works for a Lambertian world. But as I mentioned, the real world is not always Lambertian. Right? Because we have, here's the term, Lambertian. So, meaning if I have shiny structures, metallic structures, and I look at them, shiny like here, the reflexes, the brightness changes. If I see metal structures, mirror-like structures, they reflect things, it's not Lambertian. If I see glass windows, right, they are not Lambertian. So the whole man-made world has tons of structures that are not Lambertian. And then you have to ask yourself, what can I do at that point? And there's different ways you can go. You can try to model the reflectance properties of the world. That can be done, right? The BRDFs that capture the reflectance of shiny materials. I can try to infer the material parameters to simulate the light transport through windows, the diffraction, everything that you have in optics. You can try to invert that process and from the images reconstruct the 3D world, the material properties, everything. We've tried that. To some extent, you can make that work, but not in real time. Because modeling the physics of image of light transport is a very complex phenomena, and to model these in real time is just, I think, not feasible. So what can we do instead? Well, the truth is we want to track the camera. We don't care about the reflectance properties of things around us. All we care about is tracking the camera. So what we can train is we can train a neural network to tell us which areas have the brightness preserved and which areas do not, right? And it turns out you can train a network, and what you get for test images is what you see here, whereas you can see the metallic structures on the cars, in the windows, they light up, and other parts are darker. And so that basically tells the system you should rely on the darker areas to do brightness consistency checks. And so what you do is you actually downweight the residual by this what's called aleatoric uncertainty, sigma. And then obviously if you do just that here, then it will downweight everything because that will make the cost go down, right? So you need a regularizer that this is all based on a Gaussian assumption, and then you will have the log of sigma that basically says, well, you can't just downweight every pixel, right? Otherwise that term will grow large. And so in the end you have a self-supervised learning approach that can tell you depths, that can tell you camera movement, affine brightness correction, and it can tell you uncertainties. It just tells you which areas are Lambertian and which ones are not. Yes? So the good question. So the question is, how well is the depth prediction compared to depth cameras or to stereo? It's surprisingly good. There is this disagreement currently in the community. Some people say depth prediction is not so good and one should rather predict normal information. That seems to be more reliable. Or relative depths. So saying which point is nearer without giving it absolute depths. For example, obviously if I pipe in the same image from a Lego world, then it will not give the right depths. If it's been trained on the real world where things are 10 meters away, and then I give it an image of the same world but miniaturized, it will not give the right scale. And so in a way you can expect these systems, they only do what they're trained to do. And if you train in a self-driving setting on the road, it learns the size of different objects that it sees. But if you take that system into the forest, where you have leaves that can be any size, you don't know, you can have the same leaf in different sizes, then likely they will not work so well. They still work surprisingly well, but not that well. So in short, whether they work well or not is in the eye of the beholder. But I've seen recently colleagues of mine saying depth cameras are obsolete, in the sense that I can take a normal camera and run a depth prediction network on top, and I'll get something that is maybe not the same but similar, right? And I think they are obsolete for certain settings. In the self-driving world, I'd say that's solved. We can do depth predictions, and we showed it with our work and other works. That's solved. If you want something that can give you the depths for completely random environments, the forest, the jungle, that's a different story, right? So in other words, whether you can predict depths or not depends on the application scenario. if it's a constrained world, and self-driving is a very constrained world, even the geometry of the world is, for every image, the depth is practically the same, right? Why? Because the road tends to be flat, and so I can tell you the depths without looking at the image, right? And no kidding, we showed, and others also showed, that if you train a depth prediction network, it's not so easy to outperform a super naive method where you take all the training data and just average the depths, and that's the one you predict. It will give you the road, it will give you the sides, and so, it will give you a pretty good depth prediction. Apart from the actual cars that stand on the road, everything else is nicely. And that works surprisingly well. And beating that baseline was not so easy with the neural network when things started. And so this self-driving world, you see it, it's always the same depths up to, a few meters back and forth, right? And so, as I said, all of these predictions you train in a self-supervised way. Once you run it, it predicts the relative camera motion, it predicts the depths. And now here comes the clue of this method. We don't fully trust these predictions, but we use them as a prior, if you will, right? We say find a reconstruction of the camera movement and of the 3D world such that for every frame things are as consistent as possible with the predictions of the deep network. And so we feed these predictions into the loss function. And so we have a classical SLAM algorithm that's running on brightness consistency, and then we have terms in the loss function that say, well, it should all be compatible with the deep net predictions. And that increases the precision and robustness massively. And so what you see here is one of these methods running on just one single camera. No stereo, no GPS, no IMU, just one gray value camera. And as you can see, with one single camera, we can drive around the block, and this is a world that we have not seen before. This is from the test set. And you can see in comparison to the standard monocular SLAM algorithms that create a drift in the scale, here there is no drift. Things actually line up almost perfectly. And so upon publication, this work was by far the most accurate monocular SLAM system in the world. A deep learning enhanced classical SLAM system. And I do believe, often people ask me, that there is a bright future in methods and technologies that combine the best of both worlds, that take whatever they can from classical methods and they bring in whatever they can from a learning-based approach. For example, I kept saying in classes for all the classes, multi-view geometry, one of my messages was, you cannot estimate the scale of the world from one camera. I told you that, right? How in a bathtub you can film Titanic and it's going to look fairly real because, everything is scale invariant. That was actually not true. You can determine the scale of the world from a single moving camera if you know the world that you're driving through. Then a neural network can make depth predictions, and even if one prediction is not good, averaged over the whole sequence, they will aggregate to something that is very precise. And so there is no scale drift in this. And so the big benefit that the deep network predictions bring is that the depth predictions, they are metric predictions in meters, and they enter and they fix the scale over time, right? And so there is no scale drift happening here. And so we evaluated quantitatively, and not surprisingly, we found it works super well, both compared to classical methods like ORB-SLAM, or even stereo methods like stereo DSO. This monocular method still outperforms them. So you're better off with one camera and a neural network than with two cameras and no network. So this is generally the message of all these papers, is that the deep networks, they can compensate for missing sensory information. They can hallucinate whatever the other sensors would have measured, right? In fact, this is why the first method that we published, we called it DVSO, Deep Virtual Stereo Odometry. Essentially, we trained it with stereo, and the system was trained to hallucinate the second camera. And when you applied it, it would just hallucinate the second camera and give you the depths. Yes. So this is, you address one of the biggest issues in self-driving. The certification of self-driving technologies is a notorious challenge for everyone in that field. Can you prove that it's safe? There's two ways to go about proving that the system is safe. One way is that you somehow upfront guarantee that the depth prediction it makes will always be within 2 centimeters error. I believe that kind of certification is not possible for machine learning and AI algorithms today, especially not with deep networks that are to some extent black box systems that predict something you cannot guarantee that the error will be below a certain threshold. But there is a second way to certify them, and this is very practical and it works, is you run them for miles and miles and miles and you show how many errors they actually do. And then you want to do that across as wide a spectrum of applications as possible. And in particular, you want to do self-driving not just on the US West Coast, like a lot of car companies are doing, where, to my experience, it's always blue sky, it's always sunny, and the roads are sufficiently wide and the traffic is extremely regulated, but you want to also demonstrate their functionalities in places like Rome or Sicily or Mumbai or Beijing, right? Where traffic, in my experience, is significantly more chaotic and where you can have obstacles that you don't see on US roads. Especially in China, I've seen interesting vehicles with a bicycle with stuff loaded on top of it, and then if your network has never seen a structure like that, it might be very confused. Right? And so this kind of certification is happening as we speak, and that can be done. And then you may want to also drive through the forest and make sure it still works there. And so this is all solvable, and so we did a lot of evaluations ourselves on different streets, in different towns, in different environments, also in the forest or in a man-made world, and we showed it still works. But typically, as always with any deep learning method, and this for me is the biggest drawback of learning-based approaches, they do degenerate when the further away you move from your training set. This is the natural thing to expect. But how quickly the performance degrades when you move away from your training set depends on how you formalize the methods. For example, this method degrades very gracefully. Why? Because it has a classical SLAM pipeline built in. The deep net predictions, they're not taken for ground truth. They feed in as constraints. And if they are not correct, for a couple of images, that's not going to deteriorate the performance. There is an overall global optimization happening that assures that things are optimal. And so as a result, this method actually degrades very gracefully when you move away from the training data. And this is generally, I think, the benefit of hybrid methods, that the degradation, once you go what's called, once you have a domain shift, domain drift, or you go out of domain of the training data, they still often work. Now, as you can see, this is all based on depth predictions, obviously, and this was kind of puzzling to me. I suggested to my student, let's do depth predictions and feed them in the SLAM pipeline. And then this came out, right? It can track the camera very accurately, but the world is not dense, it's sparse. And then I say, wait a second, the depth predictions of the network are dense. Can you not build a dense world out of it? Well, I think for the sake of tracking the camera, he only focused on the most precise points in a way. But then we went further, and this was then a follow-up work by Felix Wimbauer and collaborators, where we focused more on the depth prediction. And so we said, take all the depth predictions and aggregate them into a dense 3D world. Because I wanted to see, can we reconstruct a dense world from a single moving camera? A very classical computer vision challenge, right? Once you do that for these self-driving scenarios, there's cars driving around, and once you predict the depths of these, but then they move over time, then what happens if you aggregate these depth predictions over time, you smear out the moving obstacle over the world, right? You can imagine. Looks really nice. I like these smeared out moving cars. But my students didn't like them. They said, we don't want any smeared out obstacles, right? So they added a module in here, a so-called mask module. And that mask module is designed to filter out objects based on lack of brightness consistency. So we use brightness consistency over several frames to predict the depths, and then we use the same brightness consistency to say if the depth is not consistent, it is likely with the camera movement that we estimated, then it's likely because some object moved, because then the color is not the same, right? So I can warp all the images based on the camera motion, and then the brightnesses should coincide. If they don't, then possibly the object moved, and we can feed that into a mask module that identifies the areas of moving objects, and these are filtered out, so the moving objects are kind of filtered out from the reconstruction. And then we get the ultimate depths module that predicts depths only for the static world and not for the moving world. And so what comes out is this technique that we called monorec for monocular dense reconstruction, and as you can see, we can recover a fairly pleasing 3D world recovered from just one single moving camera driving through the world. And here again you can ask, how precise is this reconstruction? I don't think it's as precise as a LiDAR point cloud, but the point cloud is much more dense. It's a colored point cloud, so we can actually recognize things. That's much harder in LiDAR point clouds where you see points but you don't see what you're looking at. If you have a stop sign, you can scan it with a LiDAR. You will never read what's written on it because you need the color to do that. And here we get a colored reconstruction of everything. And the precision may be not on par with a LiDAR point cloud, but it's, I would say, sufficient to do obstacle avoidance, path planning, and everything you need to drive through the world safely. What you can see is that the reconstruction, the visuals are not yet fully dense. You know, that's because the depth is predicted from one vantage point, and when you look at a different one, you have these discretization artifacts, so that it ultimately is a bit sparse. There are nicer ways to create novel views once you have the 3D camera movement, and I mentioned one of them is the NURFs, the neural radiance fields. This is a work that came out 5 years ago by Ben Mildenhall and collaborators. It made a huge splash in the community, I think partly because it was able to generate very nice, pleasing novel views. So it typically takes about 100 views or so of an object. It assumes that you have the camera locations. People often forget that. I often get asked, why do you do your 3D reconstruction? Why don't you do NURFs instead? Well, NURFs use the 3D reconstruction. They need some algorithm up front that tells them where are the cameras, right? So, and then what NURFs do is really more designed to create the novel view. Once you have the camera locations, it trains a neural network to predict for a given voxel and a given viewing direction the color that you should see there if you were looking at it. So it tries to fit what's called a light field here, the radiance field. And it trains a multi-layer perceptron to do that prediction from the voxel and the viewing angle to the color. And since it uses the viewing angle, it can actually also model non-Lambertian objects, where the color I see depends on the viewing angle at which I look at a certain voxel, right? And so this can all be trained from tons of examples. I can fit a neural network to do that prediction. And so then I can take a lot of images of objects like these, and then you can see how you can get very nice reconstructions, and they visualize it by moving the camera around virtually. But you see it's like hundreds of frames. And in comparison, as I mentioned, the rope jumping girl example that I showed was done with 16 cameras only. I think nerves do not work with such few cameras. You really need more cameras. This is one of the big shortcomings of neural radiance fields. And also they create novel views. They don't show you the actual surface geometry that's being, that there is no explicit surface geometry in the first place. It really models the light along rays and what color would you expect by integrating this up along the radiance field. And then you train a neural network to actually, using a lot of training data to predict the color and that you see of a given voxel from a given vantage point. This is work 2019 by Vincent Sitzmann. He's actually a bachelor student of mine who did a baseline work. He's now a professor at MIT. And this is the neural radiance field, and the argument of this paper is to show that they can do better. But you can see in the comparison there is a whole zoo of neural approaches that people have proposed, neural volumes, etc., to do this, to solve this challenge. You can, now one of the key drawbacks of nerves is that they are trained per instance, right? So you have an object, you take 100 images, and then you train a neural network to predict what color do I see of a given voxel from a given angle. And it does a very clever kind of interpolation in the space of light fields, if you would. But the key problem is that this neural network is trained per scene, and there's nothing it learns that would apply to a novel scene. Meaning if you get a new object with new images, you have to train a new nerve from scratch. So even though it's a learning-based approach, it's not like in the classical sense learning something from examples that would then apply in a new setting. No, you have to just, so it's really just a function fitting to estimate this light field. Whereas what you can do, and this is what we set out to do in this work called Behind the Scenes, we can train something like a density field in an egocentric perspective, and we can train it in a way that it generalizes to new environments. And so the way this works, it's a little bit inspired by neural radiance fields in that we all also use these rays, and we try to estimate the density along the ray, the material density. And but the nice thing of this approach is it is trained on training data in a self-supervised way, and it can be applied to new test data, and then you can predict the 3D world from a single image. So it's single view reconstruction, and we use density fields and we can train it. So how do we train it? Well, we use consecutive images from a video to figure out what the colors are in different positions and to determine the density that would predict this image. And once we then apply it, we can apply it to a new image and it will predict the density. Meaning for every pixel along this ray, it will tell us not only where is the object, at what distance, that would be depth prediction, but it also predicts where does the object end, right? Something that we as humans can do. If I see a car, I can not only tell you how far the car is, but I can also tell you how big is the car, because I know the car, I've seen cars before. And if you can see behind the car, that's why we call this behind the scenes, in the training data, you can learn from experience how big objects are typically. And so as a result, this is just frame by frame applying this method. On the top you see the input image that goes into it, always just one image. On the bottom you see the predictions, and you see it shows where it ends compared to depth prediction networks that don't see the end of things. Our method can see the end. Here's a mono depth, it shows you where things are, but there is only one depth per ray, whereas we, for the ray, have a whole density. And once we binarize threshold this density, we can give these 3D reconstructions that we get. Even in a completely 90-degree view, you can see a fairly pleasing, slightly maybe over-smoothed reconstruction of the world. And once you have that and the density, you can do, much like in nerves, you can do novel view synthesis, and then you get very pleasing novel views, as you see here from different vantage points. And then you can ask, does this work only on self-driving? The answer is no. So we can also show it works on random other environments, indoor or outdoor environments, where we can do density predictions that give us 3D, and we can generate novel views. Maybe something that you'll hear more about tomorrow as well, according to plan, is you can go further and do what's called semantic scene completion. So you can take a color image and you can take a depth, either from a depth prediction network or from a LiDAR scanner, doesn't matter, and then you can complete the scene. So that means you get a semantic field from a single image. That's the idea. Just the image and the depths, you get kind of a 3D semantic decomposition. And the key novelty in our case is that we can train it with only 2D losses. So we don't need a ground truth on 3D semantics. And then we can generate semantically labeled 3D worlds, all computed from a single image and depth. And here you can see the drivable area, the cars, and it's more accurate. This is the ground truth, and you can see we actually have a better reconstruction even compared to ground truth or a lot of other networks. Very often one issue with training data is that ground truth in our world is practically never perfect. And we often see what we just saw is that our reconstructions are actually more accurate than what is considered the ground truth for the given problem. All right, I think in the interest of time, I'll stop here today. As I said, tomorrow we'll get some research presentations from 3 of our students who will present what they're currently working on. Thank you very much. And by the way, next Wednesday there is no class because next Wednesday I'm organizing the Munich AI Day, which is the annual AI event in Munich, organized by the Munich Center for Machine Learning that I'm running. And so we have a lot of talks and keynote talks running all day pretty much. And so there will be no class next Wednesday, and tomorrow we'll have research presentations. A good question. Maybe you can go online if you look for the, maybe the best look for the Munich AI Day. AI Day. There may be a way to register online. I'm not sure myself how this works exactly. But do try to get in. It might be exciting to get a glimpse into what's happening in AI in Munich and the world. So we have keynote speakers coming from Cambridge and many other places. So it should be quite exciting. Thank you.